This lesson, we're going to talk about atomic math, the numbers behind the boxes in the periodic table. Now, in our last lesson, we talked about how there are indeed particles smaller than the atom. Of course, there's protons, neutrons, and electrons. That's where our focus is going to be, on those three subatomic particles. But there are even smaller ones, quarks and leptons and muons and gluons. Those are not going to be our area of focus. And the reason is atoms are by far the most important level of matter because it's at the atomic level that all of the particles of a substance become known. You retain the properties of the substance at the atomic level, but not any smaller. So, yeah, it's not the smallest particle. Yeah, there are atoms. Atoms have smaller particles within them, but it's the atomic level that really, really matters in chemistry's eyes. So that's where we're going to focus. If you were to separate protons and neutrons and electrons, you would no longer have the properties of that substance you're looking at. Okay, that brings us to the beautiful periodic table. Here's an outline of it. There are at present 118 different types of atoms that we know about in the universe. A lot of those atoms are unstable. The ones at the bottom of the periodic table are radioactive and they decay within seconds of forming, or within less than a second of forming. So really, it's the top portion of the periodic table that's most important. Elements up through number 92, which is uranium, those are the naturally occurring elements. But the periodic table is super, super important for a lot of reasons. We're going to talk a little bit about it. We represent an atom by a chemical symbol, which is either a 1 or 2 letter code. It always begins with a capital letter. And if there's a second letter in that code or symbol, then it is in lowercase. So like PB for lead consists of a capital B, capital P, followed by a lowercase b. Here's the box from one type of periodic table for phosphorus. It's got a lot of numbers in there. The chemical symbol for phosphorus is a P. Most importantly, typically it's the bigger number in the box that is the atomic number, and it's always a whole number. It's always one of the counting numbers, 1 through 118. The other number that you see in the box is called the atomic mass. Now, that's an average of several different forms. It's an average of the mass of several different forms of that element. And we'll talk about what that means in a second. But atoms can have differing numbers of neutrons and still be a type of phosphorus, for example. Some periodic tables have the element name written out within the box, which is convenient. That way you don't have to memorize symbols and what they mean, but not all periodic tables do. When we say atomic number, this is an important one, that refers specifically to the number of protons, the number of protons. And it's that number that determines the element's identity. So in the case of phosphorus, the atomic number was 15. That means that it has exactly, no more and no less, than 15 protons. If it were to somehow magically gain a proton, it would no longer be phosphorus. It would be the element with the next higher atomic number, which is sulfur. And if it were to somehow gain or lose a proton, it would become silicon with an atomic number of 14. So it's the number of protons that tells you what type of element you have. Another really important number, we call it a mass number. That's the sum of the number of protons plus the number of neutrons. Now, if you're talking about a given atom, a specific atom, you'll always have a whole number of protons and a whole number of neutrons, and you add those two whole numbers together and you'll get a whole mass number. If you're talking, however, about an entire collection of atoms of a given type, and you start to average mass numbers, that's when you can get decimals. We'll walk through an example of that in a bit. The third thing I want you to be aware of is that when we talk about charge, we're referring to an imbalance between the amount of positive charge and the amount of negative charge in an atom. Since we know that protons are the positively charged particles and electrons are the negatively charged particles, if there's a charge, that means those numbers of particles are not equal to each other. And specifically, we're going to normally assume that atoms are neutrally charged. That's most often the case, that the number of protons and electrons are the same. There's a way to represent some of these numbers. If we take a look at this chemical symbol, it's got C, and if you looked up on a periodic table, the box that has a C in it is carbon. If there is a number to the lower left of that chemical symbol, that's the atomic number or the number of protons. And you will often, if they intend to show this, they'll include a number to the upper left of the chemical symbol. That's always the mass number. So the number of protons plus neutrons added together. Sometimes you'll have a charge. So here's an example of a chemical symbol, Na. The number to the lower left is 11. That's Na's, or sodium is the name of that element. The atomic number is 11. The mass number to the upper left of the symbol is 23. So now let's think about that. If there's 23 for the sum of protons and neutrons, and we know that there's 11 for the number of protons, that necessarily means if we subtract 23 minus 11, you would have 12 neutrons in that atom. Furthermore, if there's a charge written to the upper right of the chemical symbol, it's going to be either plus or minus, or it might be like +2, which means the difference between protons and electrons is 2, not just 1, or +3 if the difference is 3, or +4, although you'd almost never see that. You could also have charges of -2 or -3. When the difference is more than 1, you put the number after the plus or the minus. So if there's a difference between protons and electrons, it will be indicated to the upper right of the chemical symbol. And when the protons exceeds the number of electrons, we have a positive charge, the difference of which is indicated if nothing's written, if no number is written after the plus, it means +1. If it's +2, that means there's 2 more protons than electrons. If there are more electrons than protons, then it's the opposite case. We'd put a minus for the charge if it's a difference of 1. We would write -2 if it's a difference of 2, -3 if it's a difference of 3. One other thing, since we assume that you have access to the periodic table at all times, it's not necessary for the chemical symbol to have the atomic number. So here's a symbol for lithium where the mass number is 7, and they can either choose to write the 3 atomic number to the lower left of the symbol, or they could decide not to. We would still know from lithium's position on the periodic table and be able to find its box and see that the whole number in that box is 3, we could still figure it out. So you don't need to list that extra number. You can have, since protons are what define an element's identity, you can have 2 atoms with the same number of protons, but they could have differing numbers of neutrons. If that's the case, we call those 2 forms of the element isotopes. Iso is a prefix that means same. So it's 2 forms of the same element. Here's an example. We have 2 atoms of neutral sodium. Notice that there's no charge written to the upper right of the Na. In the picture on the left, the mass number is 23, and the atomic number, they could choose to list it, which they did in this case, but they wouldn't have to. We could look up on the periodic table and see that sodium's atomic number is 11. So in the atom on the left, if we subtract 23 minus 11, we would arrive at 12 neutrons. In the atom on the right, the mass number is 24, not 23. If you subtract 11 from 24, you arrive at 13. There's 13 neutrons in the atom on the right side. Same element, but differing numbers of neutrons, and thus different masses. We call those isotopes. Okay, consider this. Here's a chart. I'm going to give you some symbols, complete with charges, and I want you to think about the number of protons, neutrons, and electrons. It's important to have a periodic table nearby. I'll give you a second to find that. Okay. The element with a symbol of C is carbon. Look in space 6 on your periodic table. The fact that the whole number in that box is 6 means that all of these atoms, which are consisting of the symbol C, must have 6 protons. That's the only way you could have an atom of carbon. So all the way straight down the left column, you could write 6s. To get the number of neutrons, we're going to consider the mass number. The mass number for the first symbol is 13. That means the sum of protons and neutrons is 13. And if we know that the proton amount is 6, let's subtract 13 minus 6. That gives us 7 neutrons. Now to consider electrons. Is there a charge written to the upper right of the symbol here for the first one? No, nothing is written to the upper right of that symbol C. Now that's important. The lack of a charge is really, really important. It tells us that the number of positively charged protons is balanced out by the number of negatively charged electrons. So if there's 6 protons, because you have to have 6 protons if it's carbon, then there would necessarily have to be 6 electrons to make a neutral atom of carbon. Let's look at the next symbol. Again, we have carbon, so automatically our number of protons is 6. This time your mass number is 12. So take 12 minus the number of protons, which we know to be 6. 12 minus 6 gives us 6 neutrons. And this time there is a charge. It's written to the upper right of the symbol, and it's a plus. That means there's 1 more proton than there are electrons in this atom. Since the number of protons is locked in place at 6, you must have 6 protons for an atom of carbon, then what we can write is a number that's 1 less than 6 for the electrons. The number that's 1 less than 6 is 5. There are 5 electrons and 6 protons in this atom. Let's move on to the third one. Again, if it's carbon, there are 6 protons automatically. The mass number now is 14. So let's take that minus the 6 protons we know to be there. That equals 8. The charge is minus 2. That means there are 2 more electrons than protons. Since the number of protons is locked in place at 6, we cannot change that. We can write a number that's 2 greater than 6 for the number of electrons. That would be 8. Ooh, so there's so much at play here. Lots of little things to think about. Thank you for listening, and I hope you have a good day.